Hello Calc 3 and welcome back to another video. So in this video we'll be covering the first half of section 16.2 on vector fields and line integrals. There are two different halves to section 16.2, so the second half of this video should be up shortly after I upload this one. I do warn you that both of the videos are most likely going to be relatively long, just because the section is long. And more than just that, I think the sections for the rest of chapter 16 that we'll be covering are pretty long. So just be prepared to spend some time either watching the videos or going through the notes. But regardless, let's begin here. So certain physical phenomenon that we experience, such as gravitation and electric forces, have a direction and magnitude at each point in space. So for gravitation, you can think about maybe a particle in space, or maybe just a massive object like the Earth in space, and it exerts a gravitational force on objects around it, and each of the gravitational force at the different points in space around that massive object will have different velocity or different magnitudes in different directions. And likewise for electric forces, you can think about a particle in space exerting some kind of electric force on other particles in space. And the magnitude and direction of that force will depend on the orientation of the particles, how far apart the particles are. But anyways, the force at each of these points can be represented by a vector. And this ultimately gives us a full space of vectors. So in 3 dimensions, you might have a 3-dimensional region that's full of vectors because there's a vector corresponding to each point. And in this section, we discuss how to compute the work done in moving an object through a vector field by using a line integral. And we'll go through a couple of different applications as well, more than just work done, but also flux and circulation. So again, we discussed vector fields representing velocity vectors, such as the vector field representing the flow of a liquid over a domain. And for those vector fields representing velocity vectors, that's when we'll talk about flux and circulation, specifically for fluids inside of some region. Okay, so let's get into vector fields then, define this thing rigorously. So suppose that we have a region in the plane, or we have a region in 3-dimensional space, and suppose that it's occupied by a moving fluid, for example. So the fluid is made up of a bunch of particles, and at any time, each of these particular particles have a velocity vector, since they're moving around. And the velocities at the different points can vary. So you can have one point in the fluid that's moving much quicker in some direction, and a different point inside the fluid that's moving slower in some completely different direction. But at each point, we can draw a vector that represents the velocity of that particle. And this collection of vectors makes a vector field. So it's a bunch of different vectors being associated to each point inside of some region. So in the example that I have down here, we have velocity vectors that are corresponding to the flow of air around an airfoil in a wind tunnel. So you can see that if you pick different points along the black curves that are going around the airfoil here, you're going to have different velocity vectors corresponding to the different points that you choose. But again, vector fields might also describe gravitational or electrical forces at points in space, in which case we're not talking about a moving object. But more generally, if we want just the mathematical definition of what a vector field is, a vector field is a function, a vector-valued function, that assigns a vector to each point in its domain. So remember that when we talked about vector-valued functions in Chapter 13, we talked about functions where you plug in one real parameter and the function outputs a vector. For vector fields, we're talking about functions where we input points, either in the plane or in space, and then our function outputs a vector. So this is actually a completely different kind of function. We haven't talked about it before. So in space, a vector field might look like this following equation that I have here. So the vector field here is going to be the function f, which is a vector valued function. And it's given as a function from three-dimensional space to a three-dimensional vector. So the output is going to be a three-dimensional vector. And it has three different component functions. So we have a component function m, a component function n, and a component function p. And these are all functions in three variables, so they each take inputs from space. So the vector field is considered continuous if each of the component functions are continuous. And the vector field is called differentiable if each of the component functions is differentiable. So that's just a couple of definitions to keep in mind. And in the plane, as opposed to space, a vector field might look like the following function. So we have a function f, this is the vector field here, and it takes inputs as points in the plane, and the outputs rely on these component functions m of xy and n of xy. So these component functions are just scalar functions. Or maybe I shouldn't say scalar, maybe I should say real valued functions. So they take in points in the plane and they output a real number. And ultimately, this vector field is defined as the sum of these different component functions multiplied by the standard unit vectors. So here are just a couple examples of some vector fields that are familiar to us already. We've talked about them previously in the course under a different guise. So the tangent vectors and normal vectors, which we denoted capital T and capital N from chapter 13, are actually examples of vector fields along a curve, right? So at all of the points that are on some parameterized curve, r of t, there's an associated vector. We can either talk about the unit tangent vector, which is given in red in the diagram here, or we can talk about the unit normal vector, which will be perpendicular to these unit tangent vectors. But regardless, whichever one we choose to talk about, both the unit tangent vector and the unit normal vector assign a vector to each of the points along the curve. And in that way, they do describe a vector field along just the curve. Also, here's another one that we've talked about. If we attach the gradient vector of a scalar function f of x, y, z to each point of a level surface, we obtain a three-dimensional vector field on the surface. So again, the gradient vector is a vector that's going to be assigned to each of the points on a level surface, and in that way we have a vector field that is in 3 dimensions but defined on a surface inside of 3 dimensions. So that would be another example of a vector field that we've already talked about. So here's an important example of a vector field, gradient fields. So remember from chapter 14 that the gradient vector of a scalar function f gives the direction of greatest increase of the function at a point. So the gradient field, or the gradient vector field, is the vector field giving the gradient vector at each point inside of the domain. And in that way, it's a vector field that gives the direction in which the function is increasing most rapidly at all of the different points in the domain. So here's an example where we're calculating a gradient field. Suppose the temperature T at each point x, y, z in space is given by T equals 100 minus x squared minus y squared minus z squared, and that the vector field f of x, y, z is defined to be the gradient of T. And our goal here is to find the vector field f. So to find the vector field, we're actually just going to calculate the gradient of T, and that'll give it to us. So the gradient field f is the field f equals the gradient of T, which is equal to negative 2xi minus 2yj minus 2zk, where we've just taken the partial derivatives with respect to x, y, and z respectively here to get our different component functions. And at each point in space, this vector field f now gives the direction for which the increase in temperature is greatest. So this is just a simple little example of calculating a gradient field. And hopefully now that you're comfortable with the idea of a vector field, we can move on to the real point of this section, which is evaluating line integrals of vector fields. So remember from the last video, from section 16.1, we discussed the notion of a line integral for scalar functions. Now we're going to build up the notion of a line integral for vector fields, so for vector valued functions here. So again, let f equal m of xyz I plus n of xyz j plus p of xyz k be a vector field, and assume that all of these component functions m, n, and p are continuous. And also let C be a curve in the domain of our vector field f with a smooth parameterization given by r of t is equal to g of t I plus h of t j plus k of t k. So this is just the regular parameterization of a curve that we've talked about multiple times before, where t is ranging from a to b for our parameterization. Then at each point along our curve C, we have a unit tangent vector, which is the same unit tangent vector we talked about in chapter 13. And remember that that unit tangent vector was defined to be the derivative of r with respect to the arc length parameter s. And we could also write that as the velocity vector over the magnitude of the velocity vector at each different point. And this is going to be a unit vector tangent to our curve C and pointing in the direction of the parameterization. So what do I mean by in the direction of the parameterization? I mean that as we trace out a curve in space or in the plane with respect to our parameter t, we're going to be moving along the curve in a certain direction. So we can give the curve an orientation like this. And when I say that t points in the direction of the parameterization, I mean that it points in the forward direction along the curve. So the tangent vector is always going to point this way. It's not going to point this way. Okay? And now we can move on to our definition here. So we can let big F be a vector field with continuous components defined along a smooth curve C that's parameterized by this vector valued function r of t, where t is ranging from a to b. Then the line integral of f along the curve C is defined to be the integral of the dot product of f and t over the curve C. So notice here we're defining a line integral for a vector field. In the last section we defined a line integral for scalar functions or real valued functions, and so the definition is naturally going to be a little bit different here. In this case, when we take a line integral over a vector valued function f, we have to take the dot product of that vector field with the unit tangent vector. And this will actually give us a scalar function. And once we have that scalar function, then we can apply the definition for the line integral that we already have for scalar functions from the last section. And these are a couple of different ways to write the same thing. So we could also write this as the line integral of f dot dr ds over the curve C, or we can write it as the line integral of f dot dr over C. So these are all just other ways to write the same thing. And again, this is an abstract definition, but the question is, how do we calculate these line integrals? So looking at the definition that we've given here, calculation might be a little bit difficult, it's not clear, but ultimately the method of calculation for line integrals is going to be similar to the method that we use to calculate line integrals for scalar functions. So it's going to follow this three-step process here. Let's say we want to evaluate the line integral of some vector field f equals mi plus nj plus pk along a curve in space parameterized by r of t. Then we're going to follow these three steps here. So the first step is to express the vector field f over the curve C as f of r of t. So we're looking at the vector field at the points on our parameterization of the curve. And we do so by substituting x equals g of t, y equals h of t, and z equals k of t into the component functions of f. So remember that the vector field is a function that takes in points in space, x, y, z, and outputs a vector. But x, y, z, as long as they lie on the curve, are given by the component functions of our parameterization r of t up here. So if we want f of r of t, we have to substitute g of t in for x, h of t in for y, and k of t in for z. And this will give us our vector field as a function of the parameter t over the curve c. And after we do this, the next step is going to be to calculate the derivative of our parameterization r with respect to t. And then finally, after we've done these two steps, we can evaluate the line integral with respect to the parameter t, where again, t is ranging from a to b, inside of which we've decided when we made our parameterization. And ultimately, we obtain that the integral of this vector field f over the line over the curve c is equal to the ordinary integral from a to b of f of r of t dot dr dt. So again, this f of r of t dot dr dt is ultimately going to give us a function in one variable that outputs a real value. So at this point, we're just talking about the ordinary integral from calculus 1. So as long as we can do these three steps above here and write our line integral as an ordinary integral in t from a to b, then we can just use methods from Calc 1 and Calc 2 to evaluate that integral. So now let's move on to our second example. Let's say we want to evaluate the integral of the vector field f over the curve c, where f is given by zi plus xyj minus y squared k along the curve c that is parameterized by r of t equals t squared I plus tj plus the square root of tk. And again, t is ranging from 0 to 1 in our parameterization here. Okay, so for our solution, we're ultimately just going to be following the steps that we just outlined above. So along c, x is going to equal t squared, y is equal to t, and z is equal to the square root of t. So this is just given by the parameterization of c that we have from the problem. And then we can write f of r of t by substituting in these component functions for x, y, and z. And we get the square root of t times I. So here we're taking the square root of t and substituting it for the z that shows up in our original equation, giving us the vector field f, or the original function. And then we have plus t squared times tj, where x is being substituted with t squared and y is being substituted with t. And then finally minus t squared k. So y in this component is being substituted with t, and that's where we get this minus t squared from. And then we can simplify a little bit, so we get that f of r of t is equal to the square root of ti plus t cubed j minus t squared k. So this completes the first step of our process outlined above. And now we move on to the second step, calculating dr dt. So we just take the derivative of our vector valued function r of t, and this will give us 2ti plus j plus 1/2 times t to the negative 1/2 k. And finally, we can evaluate the line integral of f over the curve c by applying this equation that we have from part 3 here. So the line integral of f over the curve c will equal the ordinary integral from 0 to 1 of the square root of ti plus t cubed j minus t squared k. So this is just f of r of t that we just found from above. And then we have the dot product of this f of r of t with the derivative of r with respect to t, which we already calculated above. And we take the dot product of these two vector functions here, or vector valued functions here. And we get 2 times t to the 3/2 plus t cubed minus 1/2 t to the 3/2. And now notice, after we've taken the dot product, this is now just a scalar function. So it takes one real value t and outputs one real value. And at this point, the integral is just an ordinary integral from Calc 1. So we can make it look a little bit nicer by combining 2 times t to the 3/2 and that negative 1/2 times t to the 3/2. And that'll give us this 3/2 t to the 3/2 plus t cubed. And now we're just finding an antiderivative for a polynomial function here. And that's simple enough, just using methods from Calc 1. We get 6/10 times t to the 5/2 plus 1/4 times t to the 4th, evaluated from 0 to 1. And that'll equal 3/5 plus 1/4, which is ultimately equal to 17/20. So that's our final answer. The line integral of our vector field f over the curve c that's given by the parameterization in our problem statement is equal to 17/20. Finally, we can move on to the last subsection for the first half of section 16.2, line integrals with respect to dx, dy, or dz. So sometimes it's nice to analyze the components of the vectors inside of a vector field in a particular direction. And in these instances, we want a line integral of a scalar function with respect to one of the coordinates. And the goal of this subsection is to define what one of those line integrals would look like. So to define the integral of, or I should say, the line integral of m with respect to dx over the curve c, so what's given here, for the scalar function m of xyz, we specify a vector field that corresponds to this m of xyz given by f equals m of xyzi. So we've taken our scalar function m of xyz and it corresponds to this vector field where we take in points in space x, y, z, and it outputs one-dimensional vectors, where those one-dimensional vectors are given by m of x, y, z. Okay, and so if we have a curve that's parametrized by r of t equals g of ti plus h of tj plus k of tk, where t is ranging from a to b, we have that x is equal to g of t over this curve, and dx is going to be equal to g prime of t dt. This is just because if we took the derivative of x with respect to t, we would get the derivative of g of t, since x is equal to g of t, which means that dx has to equal g prime of t dt. And finally, notice that the vector field f, the dot product of f with dr, can be rewritten as f dot dr dt dt, which can be written as m of xyz times g prime of t dt, and this is just equal to m of xyz dx. So the integral of m of xyz with respect to x over the line or over the curve c is equal to the line integral of f over the curve c, where f is just equal to m of xyzi. So ultimately, the construction here is not super important. If you didn't follow the construction, that's okay. You should still be able to calculate the things below. But the idea here is that if we want to evaluate the line integral of m of xyz with respect to x, so this is some scalar function with respect to x, then we can do so by associating that scalar function with a vector field that outputs one-dimensional vectors, and then apply the definition of the line integral for vector fields that we've developed in this video. So this construction also generalizes for the other components. This should not be x and y. This should be y and z. And we can just take all of that information and combine it together and box it up here. So I'm not going to go through all of these, but if you need to know how to calculate the line integral of m of xyz with respect to x over c, or n of xyz with respect to y over c, or p of xyz with respect to z over c, then you can refer to this box here. All of them are very similar to one another, and ultimately we do so just by writing that each of the scalar functions in terms of t, and we write dx as g prime of t, dy as h prime of t, and dz as k prime of t. So that's really just the key there. If you want to, you can refer to this box when you're going through your homework. That's mostly why I put it here. And then finally, for our last example for this video, let's say that we want to evaluate the integral of negative y dx plus z dy plus 2x dz over the curve C, where C is the helix parameterized by r of t is equal to cosine ti plus sine tj plus tk, where t is ranging from 0 to 2 pi. Okay, so for our solution, all we really have to do here is express all of these variables that are given inside of the line integral in terms of t. So x is going to be equal to cosine of t along our parametrized curve, y is going to equal to sine of t, and z is going to equal t, where we've just assigned x, y, and z with the component functions of our parameterization. And after we have this, then we can calculate dx, dy, and dz in terms of t as well, just by taking the derivatives of each of these functions here. So dx is going to equal negative sine t dt, since the derivative of cosine is negative sine. Dy will equal cosine t dt, and dz will just equal dt. And after we've done this, then we can rewrite the line integral as just an ordinary integral in the variable t. So the original line integral given to us will be equal to the integral from 0 to 2 pi of sine squared t dt plus t times cosine t dt plus 2 times cosine t dt, where we've just taken the functions giving x, y, and z, as well as the functions giving dx, dy, and dz, and we've substituted them into the original integral over here. So now we have the integral of 3 different summons here, and we can split that integral up into 3 different integrals for each of the summons. So first we worry about the integral from 0 to 2 pi of sine squared t dt. This will be equal to t over 2 minus sine of 2t over 4 evaluated from 0 to 2 pi. You can check that if you want that integral is correct, and ultimately that'll give us pi when we evaluate. The integral from 0 to 2 pi of t times cosine t dt is equal to t times sine t plus cosine t evaluated from 0 to 2 pi. And again, you can check this integral if you want to. And when we evaluate, that gives us 0. And then finally, the integral from 0 to 2 pi of 2 times cosine t dt is just equal to 0. And so ultimately, taking all of this information together, we get that the integral, or the line integral, of minus y dx plus z dy plus 2x dz over the curve C, which is the original integral given to us in the problem statement, is equal to pi. Okay, so that's all of the information that I have for the first half of section 16.2. In the second half of section 16.2, I'll go through applications of the line integral. At this point, you might be wondering what the geometric intuition is for the line integral, but I will give some reasons for why we care about this thing in the next video with some applications, so look out for that.